Okay, so Kartika, in the meantime, we are waiting for others to join. So I'll give you just a flashback of week 5 classes. Actually, I'm not well today, so I'll not be taking a very long class today. I'll just discuss the assignment, and if you have any query, you can discuss with me in the next class. So I'm starting with giving you a flashback of the week 5 classes. In the week 5 classes, Professor Tomar has talked about the history of the nuclear reactions and the conservation laws in the nuclear reaction along with the energetics of them. So he has talked about the first nuclear reaction, how the proton was discovered, and how we come to know that they are positively charged particles, and how did the discovery of alpha particle actually happen, and where 210 polonium was used as a projectile. Now, what is a projectile? So there are certain notations for a nuclear reactions. So first of all, we need to know there was development of accelerators, and there is a large hadron collider at CER in Geneva, which have 6500 giga electron volt proton, 27 kilometer of circumference for high energy physics experiments that happens there. Okay, so now there are certain notations. So discovery of the transuranic elements, how did they happen? G.T. Seaborg and Edwin Macmillan in the University of California, Berkeley. They actually came to know that there are something like transuranic element. Example, deuterium is bombarded over uranium, it gives neptunium with 2 neutrons. So these are the transuranic elements, and then this is what I'm talking about. What is nuclear reaction notation? Remember it, like there is a first question on this logic only, that there is a projectile, there is a target, then you get the ejectile, and there is a heavy residue. Okay, so you have helium, you have aluminium, you have neutron and polonium. So how do we write it? 27 aluminium, 4 projectile is written in the bracket at first place, 4 helium plus target is outside, and the projectile is outside. Okay, projectile is outside, ejectile is inside at the second place, and the heavy residue we get as B. So the notation can be A comma B B. Kartika, you're listening me, right? Kartika, you're listening me. Okay, so remember it. For projectile and ejectile, you have to remember this notation. So generally the projectiles are neutron, proton, alpha particle or heavy ion or the gamma rays. The target is a nucleus, and ejectile are generally gamma rays, neutrons, protons, alpha, heavy ions, and heavy residue is the nucleus. Okay, so this is it. Then he talked about nuclear reaction and the conservation law, the conservation of mass and energy. How do we find out the nuclear reaction conservation? Example, we consider 27 aluminum, helium 1 and 30p. So you can see that A comma BB, the charge is 13 plus 2 equal to 15, mass number is 27 plus 4, and mass and energy we calculate by this formula, where Q is equals to Ma plus Ma minus Mb plus Mb equal to Eb plus Eb minus Ea plus Ea, which is Q. Remember this formula, there is a numerical on it, and then linear momentum, angular momentum, parity and statistics. Okay, moving further, he talked about Q value of a nuclear reaction, which I recently talked about. If we have to calculate the Q value in terms of mega electron volt, so we have to see, suppose the notation is A comma BB, where A plus A giving B plus B, the Q can be calculated as Ma plus Ma minus Mb minus Mb. That means this is the sum of the reactants minus the sum of the product into the square of the velocity of the light, and it will give you the energy in mega electron volt. What do we multiply? Remember, we multiply by 931. Okay, so example is this, Q is equals to this plus this minus this. So if it is coming positive, it is an exoergic reaction, and if it is coming negative, it is endoergic reaction. Remember it, It's just like the heat comes out and heat comes in the endothermic and exothermic. Similarly, in nuclear reaction, they can be exoergic and endoergic. Okay, now moving further, in the second lecture, Sir talked about the energetics of nuclear reactions. Now there is a conservation of mass and energy. Suppose we have a particle. This is with mass m1 and energy e1. It is bombarding over a particle with mass m2. It is at rest. Okay, it is at rest, but it is in motion. It is getting bombarded over a heavy nuclei whose energy was initially zero. Now this heavy nuclei can do projectile motion, or can emit certain smaller particles with mass m3, e3, m4, f4 with the angle theta and phi to the normal drawn from its initial position, okay, on both the sides, either the negative side or the positive side. So the conservation of mass and energy says what? M1 plus E1 plus M2 is equals to M3 plus E3 plus M4 plus E4. Why there is no E2? Because E2 is 0. E2 was initially at rest. So sum of total of mass and energy is equals to sum of total of mass and energy on the product side. So we come across certain equation, and the quadratic equation is root of E3. Go through these. If you don't get it, write me an email. Now going further, Sir talked about the Q value of the equation in some this quadratic equation terms, and then he talked about collisions in lab and CM system. So this is what I recently told you about. Now if you have to calculate the energy, we can say that m1v is equals to m1 plus m2 vcm. So vcm from here we can calculate as m1v over m1 plus m2. Remember this formula, there are numericals on it. Okay, now collision in lab and all, this is the same thing. Energetics and all, I have already told you that how, what is exoergic reaction, what is endoergic reaction, and how do we calculate the energy. And after that, Sir talked about threshold energy of a reaction. Suppose there is a reaction with 14 and N3H12C, the Q can be calculated as sum of the reactants minus sum of the product in mega electron volt. So threshold energy we can calculate as minus Q into Ma plus Ma over Ma. So remember this. If you don't get it, I'll explain it again in this thing. So example is this. Suppose this is a Coulombic threshold. For this reaction, the Coulombic threshold will be 1.4382 Z1 into Z2 over R naught of A1 raised to 1 by 3 plus A2 raised to 1 by 3 mega electron volt. Where comes the concept of Barn unit, which I am going to tell you. Remember that threshold energy is the higher of the Coulombic and energetic threshold. So this is it. In the next lecture, Sir talked about cross section of a reaction. What is a cross section? Cross section is a measure of probability of occurrence of a nuclear reaction. It represents the cross sectional area offered by the target nucleus to the projectile for the reaction. Example is, suppose you have a nuclei with an area of pi r square. The unit is sigma, we can say, we call it barn, and one barn is 10 raised to the power minus 24 centimeters square. Now there can be neutron induced reaction or charged particle induced reaction. In a neutron induced reaction, the rate of reaction is n sigma phi, where n equal to number of target atoms and phi equal to number of n per centimeter square per second. Now if there is a charged particle induced reaction, rate of reaction equal to n sigma I, where n equal to number of target atoms and I equal to number of particles. Remember the cross section formula. And then there is a concept of angular momentum in a nuclear reaction. How do we calculate the angular momentum? Similarly to the linear momentum, there is angular momentum. Now there are two theories of calculating this angular momentum in a nuclear reaction. It can be classical, it can be quantum mechanical, and then we calculate the total reaction cross section. So go through this please, and if you don't understand, write me an email. Then there is neutron induced reaction. What do we happen in neutron induced reaction? For neutron induced reaction, sigma n, which is the cross section, is equal to pi r plus lambda whole square. So the rate of reaction is n sigma phi, n equal to number of target atoms per centimeter and phi equal to number of n per centimeter square per second. So this is it for a neutron induced reaction. What happens for a neutron induced reaction? We can generally see that the products are most often beta negative, okay, and they are mostly beta negative active, and this is mostly in the case of thermal neutrons. Remember it, NP and alpha with lighter nuclei, and they are common with actinides. There are three kinds of neutrons. One is thermal neutron, one is epithermal neutron, and one is fast neutron. When it is a thermal neutron, the energy of the neutron is less than 0.5 electron volt. When it is an epithermal neutron, it is in between 0.5 and 1, and when it is a fast neutron, it is greater than 1 kilo electron volt. Going for a cross section of neutron induced reaction, sigma n equal to pi r plus lambda square. For low energy neutrons, lambda is very higher than r. So sigma n equal to pi lambda square T naught. For low energy neutron, L equal to 0. So from here comes the Breith-Wigner formula for resonances A and gamma B, where sigma and gamma equal to pi lambda square 2IC plus 1 over these notations. They are just to be remembered. There are not many questions on it, neither in the assignment nor in this. Then there is this potential mapping. As projectile approaches target nucleus, projectile movement decreases, and then this is a plot of sigma r versus ECM. Now charged particle induced reactions are like this. Suppose you have a reaction where 4 helium plus 93 niobium giving 97 technetium which is in excited state. The Q value will be like this, the potential will be like this. As the energy is higher than 14.05, therefore for 30 mega electron volt of alpha it will be like this. So the excitation of compound nucleus gives emission of neutron, proton and gamma rays, etc. If you don't get it, I cannot explain it everything in the way. Then there is charged particle induced reaction. Initially it was neutron, then there is charged particle. In charged particle there can be protons, there can be alpha, there can be other things. So please go through them. Then in the next lecture he talked about irradiation in a nuclear reactor. Nuclear reactor is like a sea of neutrons with neutron flux in the range of 10 raised to the power 13 to 10 raised to the power 14 n per centimeter square per second. So we can write it as dN by dt is equals to nt sigma phi minus n lambda, where nt is the number of target atoms, W is the weight of target in gram, A is the mass number of target, and sigma is the reaction cross section, and phi is the neutron flux. So the solution of the above equation comes as ATI is equals to nt sigma phi 1 minus exponential of minus lambda Ti. So this is a saturation factor which comes after this stage when you go for a 0.5 thing. Okay, now you have sir have told about certain formula and certain exercises. Go through these questions, it will help you in understanding the concept more. And then he has talked about cross section of a charged particle induced reaction, and then measurement of excitation functions offline when a projectile is there and a target cation is there. How does a gamma ray spectrometry help in the AT, in the calculation of AT, and how does measurement of erectile spectra and angle distribution happens online. And then there comes the concept of types of nuclear reaction. Now there could be elastic scattering, there could be inelastic scattering, there could be direct reaction, and there could be compound nucleus reaction. Similar to the kinetics as we have studied, there can be distance collision which leads to Coulomb scattering. If there is a central collision in a target nucleus, it leads to compound nucleus formation, remember it. And if there is a grazing collision, it reacts to a transfer reaction. So if I ask you a question, what leads to what type of collision in a nuclear reaction leads to the Coulomb scattering, your answer should be distance collision. Okay, so there are questions like this in the assignment. In what is elastic scattering? In elastic scattering, projectile and target retain their identity, kinetic energy is conserved, and it can be transferred from projectile to the target during collision, and hadron is the most moderator. Then we talk about inelastic collision. What happens here? Projectile and target retain their identity, kinetic energy is not conserved. Some of the kinetic energy of projectile is transferred to target nucleus as excitation energy. So if we talk about example, particle induced gamma emissions are generally inelastic scattering kind of scattering. Talking about the third, the direct reaction, where A plus A giving B plus B, stripping reaction like D comma P, alpha comma T, alpha comma D. Example 27 Al D comma P 28 Al, transfer of a neutron from 2D to 27 Al. So these are called as pickup reaction, and they are generally used for nuclear spectroscopy in the low lying states. And then lastly, he talked about compound nucleus reaction. What happens in compound nucleus reactions? Projectile and target lose their identity. Kinetic energy is not conserved. Projectile and target fuse together to form a compound nucleus. It is a two-step reaction where a formation of compound nucleus happens and then the excitation of compound nucleus happens, and the two steps are independent of each other. Okay, so this was all about. Then there is verification of the independent hypothesis, and this was all about. This is all about the lecture of week 5 classes. So, Kartika, are you there? Okay, so like I just give you a quick flashback. If you've not taken, probably you now are familiar with the terms like water accelerator, how does the discovery of proton took place, the energetics of the reactions, and then what are exoergic, what are endoergic, the notation symbol, and how do we calculate the Q value, and the quantum chemical aspect and the classical aspect of it, and different kinds of collision happening, and then after that how many kinds of nuclear reactions are there: scattering, elastic, inelastic, compound, etc, etc. So now you know it. Now if you will go through it, you will be able to understand. If you are not, then you can write me an email. Now I'll discuss the assignment, and for those who will not attend the classes, they can at least afterwards see this, so it will be helpful for me. So yeah. So good morning, everybody. Today I will be discussing about the week 5 classes and 10 questions based on them, which will help you in solving your week 5 assignment. So my name is Shresh Gupta. As you know, my email ID is sd19ip011@iithercollege.ac.in, and today I'm taking class late, not as usual as Saturday because I'm not going well. So I'll take a very short class for the basis of week 5 classes. So yeah, going forward, the first question. Fill in the blanks X with the correct answer. 26 mg X 4He 24 Na. The options are 1H, 1N, 2D and 3He. This is a simple question on the basis of notation. Can you answer this question, Kartika? Note down the question, and I'm giving you it's 10:54. I'm giving you 2 minutes to answer this question. If you can answer this question, if not, then I'll tell you the answer. 3, 2D. Very nice. So, going to the answer, is right. Option C, 2D. Now, how do we come to know about it? We know the notation, Kartika, and for others, if they have not gone through the classes, we have a projectile, and then we have a target, then we have ejectile and heavy residue. So, how do we write it? We write the target outside, okay, 27 aluminum, which is a nucleus, and then the projectile inside, and then the ejectile, and then P30. Okay, so now if we have to see this question, so we have to see that in short, 24 plus 4, it should be 28. If you talk about like this, 27 plus 4, 31, 30 plus 1, 31. So 24 plus 4, 28, 26 is this x should be what? This x should be 26 plus 2. What makes it 28? So 2D makes it 28, therefore the option C is right. Good, Kartika. Now remember this, there is a concept of Q value of a nuclear reaction. How do we calculate the Q value? And what are exoergic and what are endoergic reactions? So going to the question number 2. The question number 2 is saying Q value of a nuclear reaction AABB is given as Ma plus Ma minus Mb minus Mb, where M is the mass of the atom. However, the Q value can be calculated using mass defect delta M values, because delta M is a measure of M, mass is conserved in nuclear reaction, mass number is consumed in nuclear reaction, or delta m is a measure of mass number. And if you can answer this question, it's good. If not, then I'll tell you after 1 minute. Okay, so you didn't tell the answer. The answer is actually the mass number is conserved in a nuclear reaction, as we know from here, from this equation, mass number is conserved in a reaction. So yeah. Going to the question number 3, N gamma reactions. N gamma means here there is N gamma, okay? N gamma, and I recently go through the question also. N gamma reactions are always exoergic because neutrons are neutral particles, binding energy of neutrons in nuclei is always positive, binding energy of neutron in nuclei is always negative, or compound nucleus reactions are always exoergic. Do you know the answer, Kartika? Option number 2 you are saying. uh, yes, it is right. Binding energy of neutron in nuclei is always positive. This is the right answer. Good. Now going for the explanations, we can see that what happens when there is a radiative capture and products are mostly often beta negative. So yeah, we can completely see from here that binding area of neutron in a nuclei is always positive. That is why they are exoergic in nature. Exoergic is what? Whose Q value is positive. Okay, so it can be only positive if the M will be positive for nuclei. So yeah, binding energy of neutron in nuclei is always positive. Going to the question number 4, cross section for neutron induced reactions are more than geometric cross section at low energy because neutron do not face any barrier. Radius of neutron can be much larger than that of target nucleus. Wavelength of low energy neutron is much larger than radius of the target nucleus. Low energy neutrons are more reactive. Okay, so I'm telling you the answer. The right answer is option number C. Wavelength of low energy neutron is much larger than the radius of the target nucleus. How it comes? Let's see. What is nuclear cross section? Let's read it, Kartika. So, and for others also, the nuclear cross section of a nucleus is used to describe the probability that a nuclear reaction will occur. The concept of a nuclear cross section can be quantified physically in terms of characteristic area, where a larger area means a larger probability of interaction. The standard unit for measuring a nuclear cross section, denoted as sigma, is the barn, and which is equal to the 10 raised to the power minus 28 meters square, or we can say 100 femtometers square. Cross sections can be measured for all possible interaction processes together, in which case they are called total cross sections, or for specific processes distinguishing elastic scattering and inelastic scattering of the latter. Amongst neutron cross sections and absorption cross sections are of particular interest. In nuclear physics, it is conventional to consider the impinging particles as point particles having negligible diameter. Cross sections can be computed for any nuclear process such as capture, scattering, production of neutrons, nuclear fission, etc. So the cross sections way is called total cross section and is denoted by sigma or sigma t. Now the typical nuclei are of the order of this. So assuming it is sphere, it has to be the order of pi r square. For example, is this. Now there are certain microscopic and macroscopic cross sections which are this. Now formally the equation above defines the macroscopic neutron cross sections. The distinction between macroscopic and microscopic cross section is that the former is a property of specific lump of material and latter is an intrinsic property of a nuclei. So we can see that wavelength of low energy neutron is much larger than the radius of a target nuclei, then only a nuclear cross section can happen. By this equation we can see from the equation that for it has to happen, there should be this process which should occur. Going to the next question. Cross section for a charged particle induced reaction approach geometric cross section at high energy, because charged particles have to cross the Coulomb barrier. It is in the third class where Professor Tomer has talked about the quantum mechanical aspect of the cross section for charged particle. Second is charged particles can penetrate the Coulomb barrier. Charged particle wavelengths are lower than radius of the target nucleus, or the ratio of the Coulomb barrier to the projectile energy becomes much less than 1 at higher energy. The option is D, Kartika, if you don't know it. The ratio of Coulomb barrier to the projectile energy becomes much less than 1 at high energy. That is why the cross section for a particle induced reaction approach geometric cross section as a very high energy. Go through the lecture number 3, you will get to know. It is just put it as a question directly from there. Question number 6. I just told you discussed this with you before starting the class. Which type of collision result in the compound nucleus formation? I expect the answer from you, Kartika, now. Distance collision, grazing collision, central collision, or deep inelastic collision? Can you tell me the answer? It's just a single line answer. I'm giving you 1 minute. I just discussed it sometime before. No, no, no. I just now told you, na Kartika. If you don't remember it, let me show it to you. This was there, na? When I told you, yeah, you have a look over this. There are types of nuclear reactions. So when there is a distant collision, it leads to compound Coulomb scattering. With a grazing collision, it leads to transfer reaction. Okay. Now when there is a central collision on a target nucleus, then only a compound nucleus formation takes place. Now the question is saying that when does a compound nucleus formation takes place? So the answer is central collision. Okay, option number C. Do you get that? Kartika, do you understood it? Hmm? Okay, great, wonderful. Now we are going to do some numericals on the basis of this class, and then we can wrap up the class. So going to the first question. The first question is saying calculate the binding energy and binding energy per nucleon in mega electron volt of a nitrogen nucleus 7 and 14 from the following data, where the mass of a proton is 1.00783 atomic units, mass of neutron is 1.00867 atomic units, and mass of nitrogen nucleus is 14.00307 atomic units. I am giving you 2 to 3 minutes if you can answer this question pretty well. If you cannot answer this question, then I'll tell you the solution. It is 11.6. I'll tell you the answer at 11.8. Okay, I'm telling you the answer now. So the step by answer can be seen as, first we have to determine the total number of nucleons. So what happens in 7 and 14, number of protons are 7 and number of neutrons are 7. So the total number of nucleons are how much? 40. This is the number of nucleons. Now we have to calculate the mass defect. How do we calculate the mass defect? 7 is the mass of proton, 7 is the mass of neutron minus mass of nitrogen nucleus. So 7 into 1.00783 plus 7 into 1.00867 minus 14.00307 atomic units. So the delta M comes out to be 0.11243 atomic units. Now we calculate the binding energy. Step 1 is determination of nucleons. Step 2 is calculation of the mass defect. Now we go to the step 3. We have to calculate the binding energy. Binding energy can be calculated as E is equals to delta M cross 931.5 mega electron volt, which states as binding energy equal to 0.11243 into 931.5, which comes out to be 104.73 mega electron volt. Now focus on the question. The question is saying calculate the binding energy. First answer is done. Now the second answer is binding energy per nucleons. Now how many nucleons we have? 40. So per nucleon binding energy will be 104.73 divided by 14, which comes out to be 7.48 mega electron volt. And the binding energy for nucleons is 7.48 mega electron volt. This is the answer. Oh, you already answered. Good. Do you want to note this question? Note the answer, or should I move further? Great. Moving further, the next question is saying the binding energy per nucleon of 7 Li3 and 4 He2 nuclei are 5.60 mega electron volt and 7.06 mega electron volt respectively. In the nuclear reaction, 7 Li3 plus 1 He1 giving 4 H2 plus 2 He4 plus Q. The value of Q is released is, what is the value of Q? It is simply on the basis of this equation that I have told you here. Follow this equation and find out the value of Q in mega electron volt. Now I'm again putting the question on the screen. This is the question. I'm giving you, you can say 2 minutes, and then you can find out the answer, and I'll tell you the solution. Okay, so let's see if you have solved something. You have not solved, so let me show you the solution. The solution is this. So the binding energy for 1H1 is around 0 and also not give in the question, so we can ignore it. Okay, now we have to calculate Q. Q is equals to twice of 4 cross 7.06 minus 7 cross 5.60. Why? You can see that. Okay, and then 56.48 minus 39.2 mega electron volt, then it comes out to be 17.28 mega electron volt, which is nearly equal to 17.3. Okay, going to the next question. Calculate excitation energy of the compound nuclei produced when 235 uranium and 238 uranium absorb thermal neutrons. Given mass of 235 uranium is 235.04539 atomic mass units, mass of neutron equal to 1.0087 atomic mass units, and then 239 U is this, and you can see how to do this question. I am straight away telling you the solution of this question. Question number 9 is 235 plus neutron giving 236 uranium. So the delta M is minus 236.0456 plus 1.0087 plus 235.0439. Remember, there is a plus sign here. There is a plus sign here, so it comes out to be 0.007, and we have to calculate excitation energy. Here we only have to calculate the energy. Here we have to calculate the Q. Now here the excitation energy, so we have to multiply it by c square, delta E equal to delta mc square. Delta M is 0.007, c square, that means they have to multiply by 931 mega electron volt, which comes out to be 6.517 mega electron volt. So the right answer is 6.517. Going to the last question of today. The customary unit of nuclear cross section is what? Barn, electron volt, AMU or angstrom? Tell me, Kartika, what is the right answer? What is the customary unit for a nuclear cross section? Okay, I'm telling you the answer. The answer is barn. What is a barn? A barn is a unit of area. It is represented by the symbol B. Originally, it was used in nuclear physics for expressing the cross-sectional area of a nuclei. So, nuclear reaction nowadays it is used in all fields high energy physics to express the cross-section of any scattering. The nuclear cross-section is measured in barn and it is equal to the 10 to the power minus 28 meters square. Nuclear reaction typically have cross-section in the range of this through a cross-section of this. Hence the correct option is barn. Okay, option number 1. The electron volt is electron volt measured if energy, and AMU is atomic mass unit, and angstrom is a unit of length, which is denoted by angstrom. So this is all. The customary unit of nuclear cross section reaction is barn. Option number 1 is right. Yes, good. So that is all for today. I'm not feeling well, so I have taken a very short class today. In the next class, we will discuss on the basis of week 6 classes, and if you have some doubts regarding today's class, you can ask me in the next class. I hope these questions solved will help you in attending the week 5 assignment, and see you next week. Till then, bye bye, take care. Do you have any question to ask? Okay. Okay then, take care.